All right. Any questions about these schedule announcements that are on screen? Yes, I have discs in my office if you want to install that. I'll go get them when you're working on an example. I've got 2 discs. You can pass them around amongst yourselves. There's 4 files on those 2 discs. A series of 2 prerequisites, the water gems file itself, and then a patch. So you'll need to have all 4 of those installed and executed. The files are numbered 1 through 4 to give you an idea of what order you should install them on your computer. I don't have the license codes though. You'll have to ask a classmate who was able to get into Bentley what license code you should use, because they keep that completely separate, all the student license codes from the installation license codes that we're supposed to use for lab machines. So I can't provide any tech support. If you want to use water gems on your home PC, I encourage that, and I think it's great. But we provide it installed on the lab computers, and that's as far as the tech support the university can provide. So we've got a busy week next week. Most of that is on Tuesday, but like I said, the report will be due on Thursday. Today we're going to continue our discussion of momentum and work through a couple more examples, and then I have a in-class exercise that we're going to work through having to do with hovercrafts. So remember that when we have a pipe that's cut with the control surface, that pressurized fluid that's on the outside of the control volume acts as though it's an external force. And so in the example we worked in class last time, the pressure and the cross-sectional area together accounted for a force that was pushing the control volume towards the right. And when we worked through the example to find what force is required to hold the system steady on that flange, it was actually to the left, because the force of the pressure times the area was greater than the momentum force. And in this case, the momentum force, since the velocity out is so much greater than the velocity in, that would ordinarily mean that for out minus in, out is to the right, in is to the right, so these are both positives, but we have a higher velocity here going out. And so the forces required in this case took into account both the pressure forces and the momentum forces. A vein, yeah?
Like on a couple of homework problems, why is this going to provide a force on the control surface, but there's homework problem for it?
Which homework problem do you mean?
Specifically the last one. Jet, like just like the last. Why is that water coming up?
Is it the wedge of water, that jet? All right, it's because all of it was just a jet that is open to the air. And so, you know, it comes out of like a tank or something like that. And as soon as it comes out of it, it's just a jet of air that doesn't have any pressure. And so where we drew the control surfaces was around that wedge. And so that the jet isn't pressurized any longer. In this case, when we drew the control surfaces, the right side of the control surface includes the jet, but the left side of the control surface is cutting through a pipe that is still pressurized. And so here we didn't have to think about, well, what's the pressure in the area, because the jet doesn't have any pressure. As soon as the water exits the tank and is in contact with the air, it instantly loses its pressure. Was there another question related to this homework problem? This one was a little bit tricky.
So I guess the velocities now, that was the part I had a problem with, trying to figure out what that velocity was.
Yeah.
I guess when you were doing Bernoulli's, you had to set your first point down towards the tank.
Well, we actually do the momentum part of the problem here before the Bernoulli's part of the problem. We've got a wedge that we know weighs 30 newtons, right? And that wedge is splitting the flow off into the sides. We don't know what the velocity is up here. We know that when the water was coming out of the tank, the water was 15 meters per second. But as the jet is going up, its velocity is decreasing. That's just what happens because of gravity. Things slow down as they're going up. And so the velocity here, the velocity is unknown, but we know it's going to be less than 15 meters per second because it's going up. By the way, what happens if the velocity is decreasing? Think in terms of continuity. Remember, A1 V1 equals A2 V2. So if the velocity here is 15 meters per second and it's going to be less than that up here because it's slowing down, what's going to happen to the cross-sectional area of the jet? It's going to be getting bigger. That's not central to this problem, but that's just something to keep in the back of your mind, is that a jet going up, because it's slowing down, the cross-sectional area will be increasing. All right, back to the main point of this one, is that we don't know what the velocity is. All we know is that that jet is going fast enough to support the wedge, and that's a 30 Newton force. And so in the momentum part of this problem, we're saying that the sum of the forces required to hold the system steady in the y direction is the mass flow rate out, the velocity out in y, minus the mass flow rate in, the velocity in y. And we're told that that's a 30 Newton force that's acting downward, holding the system steady. The mass flow rate, I think we can calculate because they tell you the diameter of the jet, right? They tell you the diameter of the jet, and since we know the velocity of the fluid and we know the fluid is water, we can find the mass flow rate by the density, the cross-sectional area, times the velocity. And so mass flow rate's known. The mass flow rate in is going to be the same as the mass flow rate out. And just to tighten things up a little bit, let me make that control volume smaller, just to make it really clear that what we're talking about is here, and then it's changing direction. So the velocity into the control volume, the velocity out of the control volume, the mass flow rate. So it's going to be the mass flow rate and the velocity out in y minus the velocity in y. And the velocity out is simply going to be the cosine of 60 degrees times v, because this is a 60-degree angle. And so that is the mass flow rate times v cosine 60 minus v, where v in. Getting split by this wedge isn't changing the magnitude of the velocity. It's still moving as fast as it was when it was going straight up. It's just changed the direction of it. And so what we have here is just one variable, v. We've got 30 newtons of force, the mass flow rate that we found from knowing the diameter of the opening and the jet velocity and the density of the fluid. So v is the only unknown, and once we find that v through the momentum part of the equation, that's when we substitute into Bernoulli's and can find h. Yes, right. And so then on the Bernoulli side of things, we've got this is going to be our location 1, and this is going to be our location 2, and so it would be the pressure head, elevation head, velocity head is equal to the pressure head, elevation head, and velocity head. And the pressure is 0 at both of them because it's a jet. We'll say Z1 is 0. And the V1 we know, the V2 we just calculated from the momentum part of the equation, and the only unknown now will be Z2. I should have written a 2 there. How many of you struggled with that problem such that you wish you had your homework back for just a few minutes? Because if you want your homework back, let's see, we get out of class at 12:50. Oh, but then you start another class, right? Yeah. Well, if you didn't solve that to your satisfaction and you want to use the few minutes between the end of this class and the start of your next one at 12:30 to work on it, then that would be fine. Just grab it from the stack after class, and you can bring it to me before your next one starts at 12:30. Any other questions related to concepts up till now? Before we move on to talking about this vane, any other momentum questions, things that have been on your mind, uncertainties? Yes? Yeah. except for in the lab, we don't worry about the fact that it's slowed down a little bit because, you know, in the lab, they're pretty close together. You know, here's the pipe, and the water comes out, and then, like, here's the first wedge, that 30-degree wedge, and it's splitting it. I mean, there is some Z1 and Z2 difference, but we're going to assume that the velocity that comes out of the jet is the same as the velocity that impacts the wedge. But it's the same calculation principle of we're going to have some force that is due to the weights that have been applied, and we're going to know the mass flow rate, and the velocity we can calculate based on the flow rate that we knew, and you'll know the angles. And so we're going to be comparing the measured weight that you actually applied to what is the force that the momentum equation says should be required to hold the system steady, and then looking at what's the percent difference there.
How close are those values?
Typically?
Yeah.
I don't remember. Let me pull it up, because I've done the calculations on these. Let me remote to my computer. All right, or if jet impact. Between 3 to 11% difference is what I got when I did this in the lab. I had an average of 3% for the 120, 11% for the 30 degree on average. I did more runs though. Overall average? 7.1% different across all of them.
No, you said you want the, what was the 50% error for each run. Average value for each deflector.
Yeah.
When you say average value, you mean for theoretical and actual, right? Average all four of those values for each run.
An average force, yeah.
So theoretical and actual average together for each run.
No, not. Let's talk about this after class. All right. Okay. So, anything related to this one or problems from the homework? All right. Let's work through this vane example. We've got a water jet with a speed of 6.6 meters per second. The mass flow rate is defined, and it's simply changing direction by a fixed vane. This is actually going to be pretty straightforward because there aren't any pressure forces that have to be accounted for. It enters with only flow in the x direction, and it exits with flow both in x and y. But it's going to be relatively simple here. It won't be the combination of any other fluid mechanics principles. We start off by knowing that the mass flow rate is 11.3 kilograms per second and that the velocity is 6.0 meters per second. In reality, a vane like this probably would slow down the velocity. You know, what we're going to be assuming is that here's the vane, and the jet that's deflected by the vane has the same magnitude of the velocity after deflection. It's 6.0 meters per second, and then still again 6.0 meters per second. But for that to be the case, that would mean that this vane is a frictionless surface, or that the fluid has no viscosity. In reality, probably contact with that surface is slowing down the flow a little bit, and so maybe the velocity as it goes out would be 5.5 meters per second. And then the response to that is that the thickness of that jet would be a little bit wider. Just for simplicity's sake here, we're going to assume that the velocity out is 6 meters per second, just like the velocity in was. Okay, so in the x direction, we're going to have the sum of the forces required to hold the system steady. And let's read the problem statement. Just to be jumping ahead a little bit, is it asking for us to find the force required to hold the system steady, or the opposite of that force? It's the opposite. It's asking, find the force of the water jet on the vane. So the question is asking, how hard is the water pushing on the vane? Where the equation that we ordinarily apply calculates how hard do you have to push on the system to hold it steady. All right? So let's keep that in mind as we do the calculations. We've got the sum of the forces required to hold the system steady is the mass flow rate out, velocity out in x, minus the mass flow rate in, the velocity in x. Okay, so we've got the force required to hold the system steady will be the mass flow rate times the velocity out, which is v times the cosine of 30 minus the velocity in, which is just v. It comes in at v and exits at v times the cosine of 30. And where v is 6 and the mass flow rate is 11.3, got 11.3 kilograms per second. We've got the v of 6.0 meters per second times the cosine of 30 degrees, and then minus 6.0 meters per second. That is negative 9.08 kilograms meters per second squared. If we take a look at the units here, we've got kilograms meters per second squared. And so that is negative 9.08 newtons. That means that the force required to hold the system steady is to the left. Therefore, the force of the water jet on the vane, force of water jet on vane, and we spell it out explicitly just to make it clear we understood that it's asking the opposite of ordinarily what the equation will calculate. Force of water jet on vane is 9.08 newtons to the right. We can circle that for emphasis. That's what's going on in the x direction. Now in the y direction, there's nothing happening as the flow goes in. There's no flow in y, but there is flow out in y. So again, we've got the sum of the forces in the y direction will be mass flow rate out, velocity out in y, minus mass flow rate in, velocity in y. Okay, the forces in the y direction will be the mass flow rate times the negative v cosine of 60 degrees. That is because, well, I shouldn't substitute in the down component of the velocity quite yet. We've got nothing flowing in. We have flow going out. So we can again put in the 11.3 kilograms per second is the mass flow rate. The velocity is negative 6.0 meters per second times the cosine of 60, or the sine of 30. So negative 6 because it's down in the y direction. Cosine of 60 will give us the component of the velocity that's downward, that's in the direction of the y. And that's going to be a force of negative 33.9 newtons. So the force is down to hold the system steady, but the force of jet on vane is 33.9 newtons up. The jet pushes the vane up. When you stick your hand out of the window as you're driving down the road, that's what you feel. You know, when you stick your hand out the window and you're sort of rotating it sideways, you can feel the thrust of your hand deflecting air downward, and so you have to push down on your hand so that it doesn't fly up. That you're applying a force downward on your hand and the fluid is pushing up on your hand in the same way that this vane operates on a jet of water. You can, sure, yeah, if you want to find a resultant force.
I mean, we already know it's
Mm-hmm. All right. This is a combination of both momentum equation and also continuity. You can see that we've got some black box. Inside of this black box is a series of vanes that we can't see, that we don't have to see, but it's redirecting flow. A jet of water comes in at 0.15 meters per second and a velocity of 60 meters per second. There's another jet over here that's coming in with a higher flow rate, 0.3 cubic meters per second, but a lower velocity, 30 meters per second. It's coming in. And then somewhere in here there are vanes that are directing some of the flow up and some of the flow down. And we're going to want to find out what forces are required to hold this system steady. And you'll notice that the flow rate is defined for one of the streams out, but not for the other. So how should we handle a case like this, where we don't know the flow rate out on that bottom jet? Flow rate in equals flow rate out. Correct. Very good. So we're simply going to apply the continuity equation and say that the mass flow rate into that black box will equal the mass flow rate out of the black box. And then once we establish what the mass flow rate out is on the bottom jet, we can apply a momentum equation. It's going to be really straightforward. So in other words, we've got this black box, and we're going to say that this is stream 1, this is stream 2, here's stream 3 coming out, and then finally stream 4 is coming in, like so. They're all going to equal out. So the mass flow rate at 3 is the one that's in question. We'll calculate that in a little bit. First of all, in the x direction, everything is already defined that we need to apply the momentum equation in the x direction. Just by quick glance, what forces do you think are going to be required to hold the system steady in the x direction? If we know that the force required to hold the system steady in x will be mass flow rate out, velocity out in x, minus the mass flow rate in, velocity in x. Is there an easy answer to be had here in the x direction? Well, the mass flow rate at 2 is double the mass flow rate at 1, but the velocity at the mass flow rate at 2 is double that of the mass flow rate at 4, but the velocity at 4 is double. They're going to be equal. The two forces are going to cancel each other out in the x direction. Let's prove that to ourselves by going through the equation here. Basically, let's see, it was mass flow rate 4 and mass flow rate 2 that we're interested in here. Mass flow rate at 2 is 2,000 kilograms per cubic meter. The liquid specific gravity is 2.0. That means that the density is 2,000 kilograms per cubic meter. And then we've got a volumetric flow rate at 2 of 0.30 cubic meters per second. That means the mass flow rate at 2 is 600 kilograms per second. And at 4, we can find the mass flow rate. 2,000 kilograms per cubic meter is the density. Multiply that by the volumetric flow rate of 0.15 cubic meters per second. And that gives us that it is 300 kilograms per second is the mass flow rate coming out, going in at 4. And the velocities are already defined. So the force required to hold the system steady will be the mass flow rate out, neither of them are mass flow rates out. So we have 0 here for the mass flow rate out. And there's more than one constituent of the mass flow rate in. So we'll do the mass flow rate in minus, all right, we've got component 4 of 300 kilograms per second, and it has a velocity of 60 meters per second, plus the 600 kilograms per second, and the velocity for that one is to the left at 30 meters per second, so that's negative 30 meters per second. (300 times 60, 600 times 30, they're going to cancel each other out. Well, times negative 30. So the sum of the forces in x will be 0. I think this may be the first problem where we've had more than one stream coming in. Okay, now in the y direction is where we're going to have to apply continuity in order to find out what's the mass flow rate of stream 3. Let's do the y direction now. All right, so the sum of the forces in the y direction will be the mass flow rate out, velocity out in y, minus the mass flow rate in, the velocity in y. The mass flow rate of stream 1 is the density of 2,000 kilograms per cubic meter, and we're given that the volumetric flow rate is 0.1 cubic meters per second. And so the mass flow rate then is 200 kilograms per second. And we can find out the mass flow rate at stream 3. Mass flow rate for 3 will simply be the mass flow rate for 4 plus the mass flow rate for 2 minus the mass flow rate of 1. In other words, we're applying in equals out here. We've got, this is out, these two are in, and then subtracting the other out from that. So the mass flow rate is 300 kilograms per second plus 600 kilograms per second minus 200 kilograms per second. The mass flow rate is 700 kilograms per second. Okay. Now applying that back over here into the momentum equation, the force required to hold the system steady is going to be, these are both outs. There is no flow in, so the second term here is going to cancel out. There is the mass flow rate at 1, velocity at 1, plus the mass flow rate of 3, the velocity of 3. And don't worry, we'll take care of the fact that stream 3 is down by assigning a negative value to that v term here. Okay, so it is 200 kilograms per second times 20 meters per second plus 700 kilograms per second times the negative 15 meters per second, which is the velocity of that jet leading out of the bottom of the black box. So this is 4,000 newtons minus 10,500 newtons. And so the net force required to hold the system steady will be negative 6,500 newtons. So we'll have to press down on that black box to hold the system steady. Why do we have to press down is because there's a lot of, the mass flow is so big coming out of stream 3. Even though the velocity is only 15 meters per second, the velocity is less than this jet velocity. Only a small fraction of the flow is going up. Only 200 is going up, and 700 kilograms per second is going down. And so the majority of the mass flow is exiting through the bottom, so we have to press down to hold the system steady as a result. All right. Well, the U.S. Navy has a series of boats called LCACs. LCAC stands for Landing Craft Air Cushion. And these are pretty amazing machines. As you can see from the image there, they have the ability to land a full-size main battle tank, or 180 troops can be on the deck of it, or they could put 4 light armor vehicles, which are themselves pretty big machines. They can go about 80 miles per hour, which is a lot faster than an ordinary ship. An ordinary ship that's down in the water faces quite a bit of resistance to moving at that speed, but an LCAC, by contrast, floats above the water. The curtain of the LCAC, when it's operating, is actually up above the water so that it has much less resistance to movement, and that's why it's able to achieve such a high velocity. And that comes at a cost, though. It burns 1,000 gallons of fuel per hour. Think about what your fuel costs would be. The engines in these LCACs, if I remember correctly, the engines are able to burn a variety of fuels, but most of the time what they'll put into it is jet fuel. It's actually a gas turbine, and jet fuel is very expensive because it has a very high octane. Jet fuel doesn't combust as easily. It burns at a higher temperature. And so, like, I was up at the Tri-State Airport a couple of months ago, and they have a flight operations office off the main building there, and they were charging something like $6 a gallon for jet fuel at that point. And so if you think it's $6,000 per hour is what you're spending to run one of those things. But when you need to take a tank inshore at 80 miles per hour, then it's your best option, I guess. So it's an interesting from a fluid mechanics standpoint as well. Let's take a look at this video, and then we'll talk about the way that the LCAC operates. was hoping that it'd show it going off at 80 miles an hour, but I don't think, let's just try this one. I can't resist. Looks like they're going fast on this one. Pretty quick, not 80. How do those things float? Look at that big truck that's coming off of it. How does something like that float? Yeah? Okay, precisely. That's exactly it. The force of the air going down is greater than the weight.
Hello, I'm Patrick Kennedy. Last year, more of our military members died by suicide than from combat. Anyone can experience stress after a traumatic event. It's up to each of us to let our...
It's just to get troops and equipment on shore quickly. Yep. Nope. Nope, but they're fast, and they can clear obstacles too. Like you know, an ordinary boat that's landing troops on shore would have to stop at the beach because it has to only go where the water is. But this could go a mile inland if it had a path free of obstacles. So it can establish a much deeper beachhead very quickly. Oh, you mean they'd shoot the rubberized cushion? Yeah, yeah. It's not like it's not a balloon. It's a pretty rigid rubber. I mean, I'm not saying that they couldn't puncture it, but it wouldn't like explode like a balloon that you get at Dollar Tree or something. Yeah, yeah. And that's one of the main operational problems with these is that over time that it's a really thick ruggedized neoprene. A UV decay will start to get it to crack, sort of like your tires. You know, if you put on $1,000 truck tires and 3 years later they're starting to get a little bit cracked or something. The same thing's true of the curtain, as they call it. So you can see from this diagram here that the engine is not only providing thrust, but also the engine is being used to blow air into the cushion. And so the way that it can lift something heavy is by forcing air down into that cushion. Now, have you ever learned a formula that allows you to relate forces and pressure and area? Like, think about this LCAC has a shape roughly, you know, like so, like a smooth rectangle, and it's pressurizing the air underneath the cushion. And so what formula do you think we could use to find out the force that it's able to lift? It's not Bernoulli's. It's actually much simpler and earlier in the semester than that. It's force is pressure times area. So if we know the area of the landing craft and we know what load we want to carry, you can very easily calculate what pressure has to be achieved inside of that curtain in order to lift it up. So in the in-class exercise we're going to do today, I'd like you to go through some of those calculations and calculate what pressure would have to be achieved in order to lift the LCAC fully loaded. Now when it's fully loaded, the LCAC can have 185,000 kilograms. 180. Oh, okay. I only printed 10 of these because I want you working in groups and it's got room for everybody to write their names. So let me get back, pair up, and I'll grab the ones. I didn't print one for everybody because I don't want you working in groups where you're actually just working individually. So there's only one paper per pair of students. Let's see. Okay, so today, let's see, we have an odd number, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 today. So we can have one group of 3, and it looks like they've already formed up. All right? picture. No, we need to go see one. They've got those out in Norfolk. We could drive over there on a class field trip to the Naval Shipyard. They've been there before. A couple of years ago they went to the shipyard. I think it'd be great. Okay, so we were going over the answers to that in-class exercise. Let's see. We find that the pressure is 0.7 psi, which is what's required in order to lift up the 185,000 kilograms. And then assuming that the wind speed coming off of each one of those blades is 150 meters per second. And I tried to get some actual data and wasn't able to find the actual data of what the wind speed is coming off of the turbines, but used some basic rule of thumb and guesswork to figure that it's probably going 150 meters per second off of the propellers. And so the total force of the two is 550,000 newtons, which would allow it to achieve acceleration of about 3 meters per second. That's 0.3 g. And just by comparison, a Ford Mustang that's going 0 to 60 in about 4.9 seconds, that's approximately 0.56 g. So it's maybe accelerating half as quickly as a Ford Mustang. So maybe it's going accelerating as quickly as a Prius or something. Yeah. Very similar. I mean, in terms of how it achieves its forward motion. Yeah. Those swamp airboats don't have a curtain, though. All right. So any questions from that in-class exercise? All right. Let's take one final look at the announcements. Remember, I said that if you wanted to grab out your homework assignment to work a little bit more on that wedge problem before the next class, that'd be fine. For the exam, bring your equation packet. I might provide a couple of additional equations beyond what's in the equation packet, but you should be familiarizing yourself with that so that you know it frontwards and backwards when it comes time for you to take the FE exam.
Do we know how many questions we're going to have?
No, I haven't written the exam yet.
Is the equation packet on, like, printed out in?
It's not. I could put it on Blackboard. All right. So homework 6B is due on Tuesday at 11 a.m. Your lab that we're going to do in class on Tuesday is the Water Gems lab. I've handed out a couple of the discs that have the installation files you need. I'll just leave it to you to share those around with one another. If you don't install it, that's fine. We've got Water Gems on the computers, the tablet computers, and also they're on the lab computers. And then the Lab 11 will be due on Thursday in class. So
We're not going to get these homeworks back for the exam, are we?
I don't know. I don't know. We've got a fast grader, but I don't know if he's going to be able to get back to you before the exam. If he does get it back to me that soon, I'll send you an email to let you know it's in the box.